We've been given the substitution to use, u equals cos x. So the first thing that we're going to do is we're going to work our way through this integral, and wherever we see cos x, we're going to replace it with u. So on the numerator, we've got 1 plus u, and in the denominator, we've just got sine x. Let's leave it as sine x for now, and we've got dx on the end. So we need to replace dx with something to do with du, so we're going to work out du by dx. So if we differentiate cos x, we've just got to think about this diagram. And remember, to differentiate, we go down in this diagram. So the derivative of cos x with respect to x is minus sine x. So we need to rearrange this to get dx the subject. So du is equal to minus sine x dx. So then we can divide by minus sine x to get dx is equal to minus 1 over sine x du. So we can replace dx with that expression. And let's times together these two fractions. So we're going to have minus 1 plus u. I'm going to write it like that, or you could write it as minus 1 minus u, or you could take this minus 1 as a factor out of the integral. But you'll see why I'm going to leave it like this for now, just for this example. Although you'd get exactly the same answer no matter how you write it. So on the denominator, if we times together the denominator, we're going to have sine squared x, and we've got du on the end now. So the only term that we've got that we don't like, which is in terms of x, is sine squared x. So we need to replace this with something to do with u. So we're going to look back at our original substitution, and we know that cos and sine are related to each other. We know that sine squared x plus cos squared x is equal to 1. So if we want an expression for sine squared x, we could write that as 1 minus cos squared x. Well, we know that cos x is just u. So sine squared x can be written as 1 minus u squared. So that helps us because then we're going to have an integral all in terms of u. So on the denominator, we're going to replace sine squared x with 1 minus u squared. So now we've just got to integrate this. The first thing that you could try is you could try a substitution. And the substitution that you would try is probably v equals the denominator. So if you did use a substitution, you would have to use a different letter. And then your aim would be to make it into a dv integral rather than a du integral. But if you tried that substitution, it wouldn't work. And actually, most substitutions aren't going to be very easy to do this. So we're going to try a different tactic. We've got one polynomial divided by another polynomial. And we know that when we've got that, we can try partial fractions. So if we wanted to do partial fractions, we're going to have to factorize the denominator, because we always need the denominator factorized to do partial fractions. So in the denominator, we've got a difference of 2 squared, so we can factorize this as 1 plus u times by 1 minus u. And normally, what we'd have to do is we would have to try and write this fraction as a over 1 plus u plus b over 1 minus u, like we normally would with partial fractions. But this example is a bit easier than that, actually, because we can divide the top and bottom of this fraction by 1 plus u. We can cancel the 1 plus u's. So actually, we don't need to go through this whole process of partial fractions, because we know that we can just write this as minus 1 over 1 minus u du. So the easiest way to integrate this is to use the kind of like quick method, which is the integral of f dashed of x over f of x is equal to natural log of the denominator. So remember, that means that if the top of a fraction is the derivative of the bottom, then the integral is going to be log of the bottom. So if we differentiate the denominator, we're going to get minus 1. So we have got that pattern where we've got the derivative of the denominator on the numerator. So here we would write this as natural log of the denominator. If you don't spot that and you wanted to use a formal method, then you could use substitution. And we just got to be careful here because we're going to have to use a new variable for substitution. So let's use v instead of u because we've already used u. So the substitution that will help us work this out is if we let v be the denominator. So v equals 1 minus u. That helps us because then our integral would be minus 1 over v, which we know how to integrate. The only problem is we've got du on the end still, and we want a v integral now, so we want dv. So we're going to have to work out dv by du. So if we differentiate v with respect to u, we're going to get minus 1. So if we rearrange this to get du the subject, because remember we want to replace du with something to do with dv, so if we rearrange this, we're going to get du is equal to minus dv. So we could simplify this integral as minus 1 over v and then replace du with minus dv. The only problem here is it looks very weird to write minus dv because remember, this is just a bit of a trick rearranging this fraction. It's not actually a fraction. dv is like an instruction to integrate with respect to v. So generally if we just had minus dv like that, we would probably write that as times by minus 1 dv. But either way, we can times this minus 1 over v by minus 1, and we're going to get the integral of 1 over v dv, which we know is natural log of v plus a constant of integration. So if we use this substitution method, we need to get back to u, because that was the integral that we were trying to work out. We were trying to work out this integral. So we're going to use the fact that v is 1 minus u. So that's log of 1 minus u. And we get the answer that we had before. So finally, if you think back to our original question, the original question only had x's in. So we want our answer in terms of x. So we're going to use the fact that u is equal to cos x. So when we work this out, it's going to be natural log of 1 minus cos x plus c.